Next, we will discuss the errors in measurement. Suppose there is a physical quantity given for which true value is A. True value of the given physical quantity is A. True value means actual value. And the measured value for the same physical quantity are, suppose, A1, A2, and so on to An. Means there are the n measurements, n number of measurements. For these n measurements, we get the values A1, A2, An that may differ from the true values. So difference is the error. If true value is not given, in that case, the mean of the measured value will be treated as the true value. That means this true value A can be calculated using the mean. Mean means we have to sum of the all measured values and divide by the number of measurement, that is n. Or in short, we can write it as summation I 1 to n ai divided by n. This is the mean value and we represent it by a bar. This a bar represents the mean. So error in measurements are, this will be delta a1, it will be equal to a1, the first measured value, minus the mean value. Similarly, error in the second measurement will be a2 minus mean value, and so on to delta an. This is the nth measurement. It is equal to n an minus a bar. This implies that in short we can write delta ai will be equal to ai, that is the ith measurement, minus the mean value or the true value of the physical quantity. Therefore, delta a mean, it means we are taking the mean of the errors. This will be equal to the sum of all the errors, and errors are to be taken positive. Therefore, we can write delta A1 plus mod of delta A2. Mod refers for positive values only, plus plus and up to nth error divided by total number of the measurement, it is n. Or in short, we can write it as summation I equal to 1 to n delta ai by n. This is the mean error. We can say it is the mean error, and because we are taking the positive, so we can say it is mean absolute error. Using this mean absolute error, we can find the relative error in measurement. This relative error in measurement is equal to the mean error delta a mean by the actual value. Actual value, we are taking it as mean value of the measurement, and this ratio is the relative error in the measurement. Here delta a mean is the mean absolute error, and a mean is treated as the true value of the quantity. Therefore, using the relative error, we can find the percentage error in measurement, and this percentage error is the delta a mean, that is the absolute mean error, divided by a mean, that is the true value, multiplied by 100. This formula is useful to find the percentage error, and questions are very frequently asked based on this concept. Next, we take the significant figures. Significant figures are the meaningful digits in the measured value. For example, if we have measured 2.345, then this has the significant figure equal to 5. Similarly, if we have measured 12.0023, this implies that significant figures are 6. And if we measured 0.003, this has the significant figure equal to 1. Then what are the rules to find the significant figures in a measured quantity? The rules are all non-zeros digits are significant. Number two, all zeros between two non-zero values or digits are significant. Number three, for number which are less than 1. For example, 0.0093. The zeros between decimal point and first non-zero digits are insignificant. That means here in 0.0093, the decimal point is having the two zeros between decimal and 9. This is the first non-zero digits. So these two zeros are non-significant or insignificant. Therefore, we can say 0.0093 has total number of the significant figures equal to 2. Only these two digits are the significant digits. Similarly, in 0.003, only 3 is the significant digit. So we say it is having the significant digit 1. Similarly, fourth point is all the trailing zeros in number without decimal point are non-significant. It means if we write 3000 and 3.000, here significant figures is 1 because there is no decimal in this number. So these trailing zeros after the non-zero digits are insignificant, non-significant. So significant figure is 1, while in the case of 3.000, the zero zeros have the decimal prior to them. So in this case, significant figures is equal to 4. Fifth is, while we multiply or divide the two numbers, in that case, significant figures in result will be equal to the least of significant figures in the two numbers. That means the number which is having the least significant figures, the same will be in the result of the multiply or division also. Similarly, sixth point, while we add or subtract two numbers, then the significant figures in the result will be equal to as many as decimal places as in the number with least decimal place. For example, if we add 2.3 and 2.575, then result will be 5784. This has the number of significant figure 1 after the decimal, and this number has the number of significant figures 3 after the decimal. That means we have to maintain one significant figure in the result also, because 1 is the least in out of the two given numbers. To maintain the one significant figure in the resultant, we have to use the round off of the digits. Here this 5 number we have to remove, and for that we round off, and we get, after removing 5, it will be 4.88. And when there is a rule of round off, we will discuss next, and when we round off this 8, then this will give 4.9. Hence the addition will be the 4.9 with the number of significant digits equal to the number which has less number of significant figures after the decimal. Now we discuss the rule for the round off. Let's take a number, say it is 5.73645. In this number, the rightmost digit is the uncertain digit, and all remaining digits are the certain digits. While we round off the uncertain digit. For example, if we want to round off the 9, then what will happen to the next digit? For that, rule is preceding digit is raised or increased by 1 if uncertain digit is greater than 5. That means if digit is 6, 7, 8, 9, then we have to increase the previous digit by 1. For example, if we remove this 9, then the round off results in 5.7364. Now, this 9 is more than the 5, therefore, this 5 will be increased by 1, that means it is 6. Similarly, if we remove this 6 by round off, it will result, because it is greater than 5, so it just increase the previous one, that means it will result in 5.7365. Now we have to remove this 5. Now we check the rule. If preceding digit, if uncertain digit is equal to 5, then what will happen? For that, if uncertain digit is equal to 5, there are the two cases. If preceding, that means digit before the uncertain digit, preceding digit is odd, then it is raised by 1 or increased by 1. Similarly, if preceding digit is even, in that case it remains unchanged. For example, in the above example, if we want to remove this digit 5, we have to check the previous digit, and it is even. Even are the numbers which are divisible by 2. So as per this point 2, if preceding digit is even, it remains unchanged. That means we will get 5.736. And in this way we can proceed further. So this is the way we can round off the uncertain digit.